Hello, everyone. Um, I don't know if anybody here was in Brussels, but there I had a workshop in the FHE Summit on crash course in TFHE, and this one I'm gonna try to give an intro to MPC decryption in fhEVMs. Of course, before moving forward, I need to tell about some basics and also some basics about fhEVMs and some technical intro, and then the threshold decryption, and then I'm going to conclude my talk. So as probably almost all of them and all of you are aware, FHE fully homomorphic encryption is a cryptographic primitive that allowing us to compute on encrypted data, because in regular and traditional encryption schemes, you cannot compute on encrypted data, right? Like you encrypt the data, transfer the ciphertext, and then the recipient decrypts the ciphertext and get the plain text data. But thanks to FHE, now we're able to compute on encrypted data. This is very useful in terms of several things, of course in payments, salaries, and stuff like that. Also, one other really important use case is healthcare, because no one would be willing to reveal their healthcare and finance data. Yeah, of course, the advantages, data confidentiality. This is actually the goal, and also this really gives us some versatility, because we have both confidential machine learning, but also confidential voting, confidential payments, confidential finance, confidential healthcare. So I think this is also really promising. But of course, we have also some challenges. The first one is, of course, the performance overhead. FHE still is a baby in terms of cryptography, and FHE operations are computationally costly. So we're actually trying to do everything to reduce this computational cost, and we're waiting for the hardware acceleration to make it more efficient. Also, noise management is coming from the nature, because almost all the FHE schemes are based on the cryptographic primitive we call learning with errors, which was proposed by Regev back then. Learning with errors basically is a principle that adding some noise terms into vectors or polynomials depending on the scheme, so that making the ciphertext tough to decrypt. So almost all the cryptographic encryption schemes are based on some tough problems, and in LWE the noise management is the hardness assumption. Okay, so then what is fhEVM? fhEVM, as the name suggests, FHE enabled Ethereum virtual machine, and it combines the cryptographic techniques of FHE with the functionality of the EVM to enable confidential blockchain for EVM-compatible chains, basically. Yeah, the main features are, of course, the privacy-preserving computations and also the integration with EVM. As I just mentioned, we can skip through that quickly. Yeah, these are quite promising use cases, actually. The first one is encrypted ERC20 tokens, or what we so-called confidential ERC20. I'm hoping that you all were aware of our latest collab with Circle on confidential ERC20. If not, please check it out. The other is, of course, blind auctions. Normally, by the nature of blockchains, as they're transparent, both auctions, votings, and token transfers are totally public and transparent. But thanks to FHE, now all of them are possible to implement without compromising the confidentiality. Okay, so we have FHE is a cryptographic primitive and cryptographic method, right? Top field of cryptography, let's say. So we're encrypting something, they're decrypting something, but in between we're also computing on ciphertext. But if you have the keys, it's easy to encrypt and it's easy to decrypt. But in the blockchain stuff, when we add the decentralization sauce into the soup, then things get complicated, because if this is a one-party setup, it's really easy because you have the public key, you have the secret key, so you can both encrypt and decrypt, right? But in the blockchain setup, you cannot trust any single party. So like we needed to find a way to decentralize the system. And MPC was the solution here. MPC, standing for multi-party computation, is like used for, in this case, used in the decryption process because we don't need it in encryption because like users are already, responsible with providing the encrypted data to the global state of the blockchain. But to decrypt any ciphertext, we need the MPC network or like validators to agree on a fact that some ciphertext belong to some particular user, so that when that particular user requests a decryption, and if like let's say 70% of the validators agree on the fact that okay, that user is the actual owner of the ciphertext, okay, we are granting access and we are decrypting. But each validator or like each node has only a share of the secret key of the network. None of them has the entire key because that would leak a crucial information regarding everything in the setup, like the funds and the other stuff. So every single party holds a share of the secret. Then here the secret is the share of the secret key. So two things here. First, distributed key generation, and the second is threshold decryption. Distributed key generation is, as the name suggests, of course they have a really big cryptography background, but like in a simpler sense, when you first generate the keys, like you never create like the secret key as a whole, but like create its shares like as the number of validators and distribute them to among the set of validators, and then public key of course is public and we don't have any problem with that. The second part is threshold decryption. So why threshold? Because we need fault tolerance. Like, okay, we have let's say 100 validators, but if 5 of them, 10 of them, even 15 or 20 of them could like could disconnect from the network, and we cannot risk any any missing in the secret because that would end up the entire setup. So we need fault tolerance. That's why we have a threshold setup here. And of course, this threshold can be set at the very beginning of the setup, and in FHEVMs it's 70%. So if 70% of the validators are like agree on the fact, then that is executed. So where to start? Okay, this is Shamir's secret sharing, like the starting point for threshold and MPC decryption in cryptography. Not sure how many of you are familiar with like polynomials and modular arithmetics, but like basically we were given a secret S, and in this setup S is a number, and then we have a method to split this share into multiple parties, and we're using a polynomial for this, and like f of x, a0 plus a1x, and goes like that till a t minus 1 x to the t minus 1 modulo q. This is the polynomial, and a0 here is the secret, let's say the secret key, or s, as noted here. And here, let's assume, okay, I'm going to get back to this. Let's assume we have like 5 parties. We calculate and evaluate this function on like 0, 1, 2, 3, 4 points, like on 5 points, and we distribute the numbers and the outputs to these nodes. Let's say, okay, we have 5 owners, share owners, and those owners have only like 0, 1, like 1, 15, and stuff like that, only pairs. And when we want to reconstruct the secret, we use a well-known mathematical method we call Lagrange interpolation. This looks complicated, but it's really not. Like, there is also geometric intuition. So let's say we have 5 secret owners, and they only have a minimal knowledge, which is not sufficient to reconstruct the actual secret. And in this setup, if 3 of the 5 owners get together and like provide their points, let's say 0, 1, 1, 15, 2, 30. I'm just making the numbers up. And when you apply those three numbers, Lagrange interpolation, you got the secret. And it doesn't matter which 3 or 5 do this. So this is a really, really useful method to implement threshold secret sharing. This was proposed by Shamir. He was a genius, like one of the people behind the RSA also. Yeah, this is also an example. Maybe you could test it out by yourself. This is a really basic example, by the way. We never use these numbers. We use way bigger modulus, like moduli, like 2 to the 64, let's say. But just out of just for the sake of simplicity, we can take this. And yeah, when we apply Lagrange interpolation, we get the secret back. So okay, this is the first starting point. Of course, I think there are more simpler, like much more simpler methods of secret sharing as well, but like they're quite irrelevant to the main point. The FHEVM, specifically the one built by Zama, uses another scheme called linear secret sharing. It's based on vectors and linear algebra, not polynomials, but as it's quite difficult to explain here in 30 minutes, I wanted to start with this one, but it's really close. What about, okay, this was the theory. What about the FHE version of it? So TFHE is the FHE scheme that we use in the FHEVM, right? And the ciphertext is the basic LW ciphertext, input of TFHE. S here is the secret key, E is the noise, and A is sampled randomly. Delta is the scaling factor, like the moduli, like modulus, plain text modulus over ciphertext modulus. Oh no, the opposite. And M is the message. This is how we encrypt a message in TFHE. Of course, before this one, we encode the message. Like if the message is like the bit 0, then we encode it to, let's say 0, but 1 to 1 over 2. And then we apply this equation to encrypt the message. And here, the pair B, comma A or A, comma B is the ciphertext. How we gonna decrypt this ciphertext, but in a threshold setup, not a single party setup? It's quite similar to what we just saw. Like we split the secret key S into like n different shares, and like those, and of course we're requiring at least T out of n validators to collaborate to decrypt the ciphertext. Each validator holds a share Si. Notice that this Bi is actually equal to delta M plus E, right? Like the noise plus message if we disregard the scaling factor. And then once the validators come along to like put together all the I's of them, they got the delta M plus E, but like as E is randomized for each one, those E's are canceled, and after the Floor operation, message is revealed. This would be the most basic case, but of course this is not in the production. That's like, it's actually good practice to think about why, like why we are not directly implementing this. Why is the following? Because when we do this, secret key is revealed, right? And we don't want to do it because we're gonna use it again and again, like all the time. That's why we're introducing another noise. We love to add noises in FHE. The capital E. This is called noise flooding in the cryptographic manner. We're adding another random noise to each secret share. And when the operation is done, like the threshold operation is done, what we have here is delta M plus E plus the capital E. Here is the random noise term added by each validator. And to like how are we gonna get rid of this E? Of course, like when we apply, of course, it's like 1 over scaling factor times like when we add them up all the BIs. As delta E, as the capital E is also randomized factor coming from each validator, they also cancel them out. at the end of the procedure. So this is a dummy example for this one as well. Of course, I couldn't put every single step because like it would exceed the amount of slides, but you could also try it by yourself. It's fun. And yeah, as I said, when we apply the final decryption procedure, the message is recovered without revealing the secret key. This is actually really great because, like, okay, we are revealing the message, which we really need. Like, we really only need the M, right? We don't actually need the secret key itself. We want to use it, but we don't need to know it. And threshold setup and the MPC makes it possible, and I think this is something really, really, really clever. Yeah, and this is how like naively the threshold decryption setup works.